Today I'm going to talk about rolling, torque and angular momentum. We're going to talk about rolling motion first. Rolling motion we will consider to be happening without any slip, so smooth rolling. The center of mass of the object is going to be moving on a straight line parallel to the surface, and the object will be rotating around the center of mass as it is moving. So if we look at the example here, which is a bicycle wheel, the center of mass is located at the axle of the wheel, and as the wheel is rolling, the center of mass is moving to the right with velocity vcom. At the same time, a point P on the circumference of the wheel will rotate through arc with length S as the wheel is moving. And so an angle theta will be subtended between the two positions of that point. So we already know from the previous lecture on rotation the relationship between the length of arc S, the angle theta, and the radius of the wheel. So the length of arc S is equal to the product of the angle theta and the radius of the wheel R. We furthermore also know a relationship between the linear velocity vcom of the center of mass and the angular velocity omega, and that is given by the product of omega and the radius of the wheel R. Similarly to projectile motion, we can consider rolling motion to be the combination of two independent motions. So first we have pure rotation, for which every point on the circumference of the bicycle wheel has a linear velocity, a linear speed equal to the speed of center of mass vcom. And the other type of motion is pure translation, for which every point on the wheel translates with velocity equal to vcom. So for the pure rotational part of the motion, right here, the top point T on the wheel has velocity vcom to the right. The bottom point P has velocity minus vcom to the left. So when we put those two motions together, we get rolling motion. And adding the velocities as vectors for the top point T, we get that the velocity of the wheel of a point T at that point is equal to twice vcom. The axle is moving with velocity vcom, as we know, and then at point P we have zero velocity, because from the rotational part of the motion we have minus vcom velocity, from the translational part of the motion we have plus vcom velocity, so the sum is zero. So for a rolling object, the point of contact with the surface along which the object is rolling is instantaneously at rest. Here is an actual picture of a bicycle wheel which is rolling on a flat surface, and as you can see, the spokes here around the point of contact with the surface are visible as if they are still in place, as opposed to the rest of the wheel where the spokes are blurred since they are moving with some velocity. Now let's talk about the kinetic energy of motion for a rolling object. Well, we have two motions combined, as stated already. We have rotational motion and we have translational motion, which means that we are going to have two terms in the expression for the kinetic energy of a rolling object. We're going to have a term that corresponds to the rotational kinetic energy, and we are going to have a term that corresponds to the translational kinetic energy. So as the bicycle wheel is rolling to the right here, the rotation is in clockwise direction. And so in order for the wheel not to slip on the surface, there must be a force present there, and that is the force of static friction, Fs. Why do we have a force of static friction? Well, remember that this point P is at rest. That's the point of contact between the wheel and the surface. So this point is at rest instantaneously. So then why the direction of the force of friction is like so, to the right here? Well, if you look closely at the surface, indicated with black here, and the part of the wheel with blue, when point P is in contact with the surface, the relative motion of the wheel with respect to the surface is to the left, which then, in turn, is going to generate a force of friction to the right. So that is the force of static friction there. And because of that relative motion of the wheel with respect to the surface, the force of friction is directed to the right. Now let's look at a more specific example of rolling, and that is the example of a ball or a sphere rolling down an incline. So first of all, rolling is a motion that occurs without slipping. If there is slipping, then obviously we can't use this example to talk about the acceleration with which the ball or sphere is rolling down the incline. So since there is no slipping, that means that there is a frictional force, which would be the static friction force, that acts up the incline. If there was slipping, then the sphere will be sliding down like so, and then there will be kinetic friction force up the incline, opposing the direction of motion, or opposite the direction of motion. Since there is no slipping, that force of friction is up the incline, but it's static friction force. So if I wanted to derive an expression for the acceleration of the sphere, I need to use Newton's second law for translation and then also for rotation. So what forces are present here in this particular problem? So we have the weight of the sphere pointing straight down towards the center of the earth. And then we have the normal force perpendicularly up from the incline. And the normal force is balanced by the y component of the weight of the sphere. And then the x component of the weight of the sphere is causing the center of mass of the sphere to go down the incline, and the presence of the static friction force is causing the sphere to roll. So in x direction, which we are going to take positive orientation to be up the incline, we have two forces that act on the sphere. That is the x component of the weight applied to the center of mass, and the static friction applied at the point of contact between the sphere and the incline. And in y direction, we have the normal force and the y component of the weight, which balances it. So let's write the equation for the net force in x direction. So the equation for the second law, for the linear part of the motion, states that the static force of friction minus the x component of the weight of the sphere is equal to the mass of the sphere times the acceleration of the center of mass of the sphere. Now, to that, here I have two unknowns. I have the force of static friction is unknown, and I'm looking for the acceleration of the center of mass. So that means that I must first determine what is the force of static friction. I can determine the force of static friction from the rotational equivalent of Newton's second law. The rotational form of the second law states that the torque of the force of static friction which is the product of the radius of the sphere and the magnitude of the force of static friction, so r times Fs, is equal to the product of the moment of inertia of the center of mass of the sphere times the angular acceleration with which the sphere rotates. Rearranging the terms gives me that the force of static friction is equal to I,, times the angular acceleration alpha divided by the radius of the sphere. So then substituting the angular acceleration alpha with its relationship through with the acceleration of the center of mass through the radius, I finally get that the static friction is equal to the product of the moment of inertia of the center of mass I,, times minus A,, x divided by r squared. So the minus here appears because the acceleration of the center of mass is down the incline, which is in direction opposite to the selected positive direction of the x-axis. And furthermore, the angular acceleration is the rotation is in counterclockwise direction here, therefore the angular acceleration is a positive, has a positive orientation for the rotation. So now I can substitute the expression that I just got for the force of friction Fs into the second law equation for the linear part of the motion and rearrange the terms to get an expression for the acceleration of the center of mass. So minus I,, times A,, x over r squared minus mg sine of theta is equal to ma, x. So from here I'm going to rearrange the terms to express the acceleration of the center of mass with the other quantities. So I get that the acceleration of the center of mass I,, x is equal to minus g sine of theta divided by 1 plus I,, divided by mr squared. So that is this expression here in the green box. So notice that I left the term for the moment of inertia of the center of mass without actually writing down the its expression for the sphere, because this formula for the acceleration of the center of mass is applicable for any rolling object. So for any rolling object, I can use this formula to calculate the acceleration of the center of mass down the incline. I only need to replace the term for I,, with the appropriate value for the moment of inertia of the center of mass. And so for symmetric objects such as spheres, spherical shells, cylinders, and rings, all of these are known from the table in the chapter of rotation. The term I,, divided by mr squared is the term that appears in the expression for the acceleration of the center of mass due to the pure rotational part of the rolling motion. If the rolling motion wasn't there, if the rotational motion wasn't there, then that means that the object will be just sliding down the incline. And then in this case, we already have seen that the acceleration of the center of mass is simply equal to minus g sine of theta. And this is due to the x component of the weight only. In the lecture on rotation, we discussed torque for a rotating body about a fixed axis. And I mentioned there that torque is a vector quantity and is the result of a cross product of two vectors, a position vector and a force vector. Now let's look at torque for an individual particle that can move along any path but relative to a fixed point. Furthermore, the path doesn't have to be a circle. It can be a random trajectory in space. And now we are going to talk about torque as a vector quantity. So we are going to consider a right-handed coordinate system with x, y, and z axes. And if we take a particle that is located at point A in space, the position of the particle at that point is given by the position vector r. And so that particle is under the action of a force F, and the direction of that force F makes an angle phi with the direction of the position vector r. So we know already that only the radial component, which here is labeled with F perpendicular, is going to cause rotation about this fixed point here at the origin of the coordinate system. And so therefore, the torque that this force will generate at point A of that particle will be by magnitude equal to the product of the length of the position vector r and the length of the perpendicular component of the force, so that is F sine of theta. But this again is the definition of a cross product. So I can rewrite the expression here as the torque is a vector is equal to the cross product of the position vector times the force vector. So the expression here defines the magnitude of the torque vector. The expression here defines the torque vector as a, in general, three-dimensional vector in space. Now notice also that since the torque is the result of the cross product of two vectors, the torque is a vector that's perpendicular to the plane that contains those two vectors. So vectors r and f are in the xy plane, and so then the torque vector is perpendicular to that plane, and therefore the torque vector is along the z-axis in the three-dimensional coordinate system. Since we are dealing with a cross product, then the direction of the resultant vector of the cross product of two vectors is determined by the right-hand rule. So if we place the fingers of our right hand in the direction of the first vector in the cross product, and then we rotate the fingers towards the direction of the second vector in the cross product along the angle between the two vectors, the thumb of the right hand should point in the direction of the resultant vector. And one more time, the magnitude of the torque is equal to the magnitude of the position vector times the magnitude of the perpendicular component of the force that acts on the particle. Due to the fact that sine of phi can be transferred to and grouped with the position vector magnitude, I can also consider that I'm multiplying the magnitude of the force F applied to the particle and the magnitude of the perpendicular component of the position vector to the line of action of the force F. So both interpretations give me the same result, and so both interpretations can be written like equation 1116 or equation 1117, and they both give the magnitude of the torque acting or generated on the particle from the applied force F. So far we talked about the correspondence between various rotational variables or quantities and their linear counterparts. We've talked about the angular velocity, angular acceleration, moment of inertia. We talked about torque. We have not talked about the counterpart to linear momentum for rotational motion. So this counterpart is called angular momentum. The angular momentum is a physical quantity that only makes sense to be calculated about a fixed point in space. So in the cartoon here on the right, if I take a three-dimensional coordinate system x, y, and z and place a particle that moves in space at point A, I can calculate the angular momentum of this particle with respect to this point O by taking the cross product between the linear momentum of the particle at that moment of time and the position vector of the particle at that particular point in space. Similarly to the discussion about torque, here it only makes sense to take the perpendicular component of the linear momentum, P perpendicular, and multiply it by the position vector component. And so, if I do that, I'm going to get the magnitude of the angular momentum, which would be equal to R mv sine of phi. This again is a form, an expression here that corresponds to the expression for the magnitude of the cross product of two vectors. So the cross product of the position vector and the linear momentum vector gives us the angular momentum vector. And so by magnitude, when I multiply those two components, I get the magnitude of the angular momentum vector. So the cross product itself looks like so. The angular momentum is equal to the cross product of the position vector and the linear momentum. Or in other words, that's the mass of the particle times the cross product of the position vector of the particle and the linear velocity of the particle. The units for angular momentum are kilogram times meter squared per second. So when I'm calculating the magnitude of the angular momentum, I can again look at the product of the magnitude of the position vector and the perpendicular component of the linear momentum of the particle. Or I can also look at the product of the magnitude of the perpendicular component of the position vector and the magnitude of the linear momentum of the particle. So this is shown in this second cartoon here down in the right corner. So here we have the linear momentum of the particle as it moves in space, and here we have the perpendicular component of the position vector to the line along which the linear momentum vector lies. So when this perpendicular component of the position vector is expressed in terms of the position vector itself and the angle phi, we get the same relationship for the magnitude of the angular momentum. To find the direction of the angular momentum, one more time, use the right-hand rule. So in this case, the vectors, the position vector r and the velocity vector v will be both lying in one coordinate plane. And then the angular momentum vector will be perpendicular to that plane. So we must place the fingers of our right hand in the direction of the position vector r, then rotate towards the direction of the velocity vector v along the angle between the two vectors. The thumb of our right hand will point in the direction of the angular momentum vector. In order to apply the right-hand rule here, simpler than the drawings that are shown on this previous slide here, I'm going to translate the velocity vector so that the both vectors start at the origin of the coordinate system. And then when I apply my right-hand rule, the fingers of my right hand are directed along the direction of the position vector. Then I will rotate towards the velocity vector, and then the thumb is going to be directed in the direction of the resulting angular momentum. And so in this particular example, the direction is along the positive z-axis. So since the angular momentum is directed in positive z direction, that means that when I'm doing calculations with angular momentum, if I have to consider the magnitude of the angular momentum, I must take that value with a positive sign. If the angular momentum would was pointing in negative z direction, then for calculations with the magnitude of that angular momentum, I would have to take negative sign in front of the value. So then this concept of angular momentum about a fixed point in space without a requirement for actual circular motion around that point for a moving particle means that I can calculate the angular momentum of a particle that is moving along a straight line with respect to a fixed point in space. So let's look at a particle with mass m moving to the right here with velocity v, and I want to calculate the angular momentum with respect to this point O. So what I need to know is the perpendicular distance between point O and the direction of motion, or the line along which the momentum of the particle is directed. So I need to know this distance. I will call it r. And so by the definition of angular momentum for the magnitude, I get that L is equal to mRV sine of 90 degrees, since the angle between r and the line along which lies the linear momentum of the particle is 90 degrees, and so that's simply mvr. In the lecture on linear momentum, we talked about Newton's second law in the form F is equal to dp dt. So the force acting on an object or a particle was equal to the time derivative of the linear momentum of that object or particle. Well, here we can apply the same idea for the rotational counterparts of those linear quantities. So the net torque is equal to the time derivative of the angular momentum for a particle. One important detail that you must be aware of is that both the torque and the angular momentum must be defined with respect to the same point in space. So if I calculate the angular momentum for one particle in a system of particles, then I can do the same calculations for all other particles in that system. And when I add all the angular momenta, L1, L2, L3, and so on and so forth until Ln, that will give me the total angular momentum of the entire system of particles. So then, on the other hand, I can also calculate the net torque that acts on each individual particle and add all of those together. And so if I take the time derivative of the total angular momentum, then I'm going to get the net torque that acts on the entire system of particles. Or in other words, the net torque acting on the system of particles is equal to the time derivative of the total angular momentum of the system of particles. So this is just a generalization from one particle to infinite number of particles. Notice also that those individual angular momenta for each particle are calculated with respect to one fixed point in space, but those particles are moving along random trajectories. So these angular momenta vectors are not all aligned along the same coordinate direction. They are directed in random directions in three-dimensional space. From the consideration that the torque and the angular momentum must be measured relative to the same origin, follows that if the center of mass of a rigid body is accelerating, then the origin must be on the center of mass. So then for a rigid body, we can find the angular momentum by summing the angular momenta of all individual particles with respect to the center of mass, essentially. Well, it can be any other point, really. What we must realize, though, is that we are always going to get the z component of the angular momentum. So since we are working in three-dimensional coordinates, the motion will always be about the origin of that three-dimensional coordinate system, and typically we take the motion to be in the x and y plane, and so therefore, as a result, the angular momentum of every particle that makes this rigid body will be directed along the z-axis, and that's why we label the angular momentum as Lz. So for each particle in the rigid body, we are going to have a component of the angular momentum, which will be along the z-axis. And then from the definition of the angular momentum, we get the mass of each particle, delta m, times the velocity of each particle, times the perpendicular component of the position vector to the trajectory of that particle. And after replacing the linear velocity of each particle with its relation to the angular velocity of rotation, omega times r perpendicular, I end up with this product. So the angular velocity, which is constant for all particles, no matter where they are with respect to the axis of rotation inside the rigid body, times this term here, which corresponds to the moment of inertia for each individual particle of the rigid body. And so then this product becomes simply the product of the moment of inertia of the entire rigid body times the angular velocity of rotation about that fixed axis in space. And so finally, the angular momentum of a rigid body is equal to the product of the moment of inertia of that rigid body about that fixed point in space times the angular velocity. So the discussion on the previous slide is illustrated in this drawing here. We have our rigid body with random shape, which rotates about an axis that passes through the z-axis of the three-dimensional coordinate system x, y, z. For a particle inside the rigid body with mass delta mi, I can calculate the angular momentum. So the particle is a distance r perpendicular sub I from the axis of rotation. The linear momentum of the particle is pi. And so then multiplying the mass of the particle, the position, the distance from the axis of rotation, and the magnitude of the linear momentum gives me the magnitude of the angular momentum for that particle. Then I can perform the exact same operation for all other particles, sum the results, and I end up with this general result for the entire rigid body. So here in this table, we have another match between linear and rotational variables or quantities. So for translational motion, force, we have force. For rotational motion, we have torque. And so torque is a vector quantity that's equal to the cross product between the position vector of a particle in space and the force vector that's applied to that particle. The counterpart to linear momentum is the angular momentum, which is the cross product between the position vector of a particle in space and the linear momentum of that particle. The linear momentum for a system of particles, which is just the sum of momenta of the individual particles, is the linear counterpart to angular momentum or a total angular momentum for a system of particles that rotate in space. The linear momentum expressed as a product of mass and velocity of the center of mass has a counterpart in rotational motion, which is the angular momentum expressed as a product of the moment of inertia and the angular velocity of rotation. Newton's second law for linear motion is expressed as the net force equal to the time derivative of the total linear momentum of a system of particles. For rotation, we have that the net torque of a system of particles is equal to the time derivative of the total angular momentum of a system of particles. We also have a conservation law for linear momentum. We stated that the linear momentum of a system of particles does not change if there is no external net force applied to the system. For angular momentum, we have the same conservation law, which states that the linear momentum of, the angular momentum of a system of particles does not change, is conserved, if there is no external net torque applied to the system. So this statement means that the net initial angular momentum of a system of particles will be equal to the net final angular momentum of a system of particles. So in other words, if the net external torque on a system is zero, so the angular momentum of the system remains constant, and it doesn't matter what changes take place within the system. Since these are vector equations, and in general they are three-dimensional equations, we can then separate along each coordinate axis and restate the above statement as if the component of the net external torque on a system along a certain axis is zero, then the component of the angular momentum of the system along that axis cannot change. And that's doesn't matter what changes take place within the system. So this can be expressed in terms of moment of inertia and angular velocity with this relationship here given by equation 1134. An example of where this relationship applies would be an ice skater. So if you've observed ice skaters spin in place, they can change the angular velocity with which they rotate about an axis that passes through the center of their bodies by simply extending or pulling in their arms. So when the arms are pulled in, the angular velocity, let's say the initial angular velocity is large, so the skater would rotate very fast, and that is because they have small moment of inertia. Once they extend their arms out, their moment of inertia increases, and since there is no external net torque applied on the skater, their angular velocity must decrease to keep the product of the two the same as before. So this is an example of conservation of angular momentum. Another example of conservation of angular momentum is the rotation of planets about or around the sun. So the orbits of the planets are not circular. In general, they are elliptical. And so the conservation of angular momentum, it was proven that it follows from the conservation of angular momentum, it follows that for the same amount of time, the planet as it moves along the orbit sweeps the same amount of area around the sun. So if this is the sun right here, this is the planet orbiting around the sun on an elliptical orbit. The statement is that for the same amount of time of motion, the planet will sweep the same area around the sun. So the area here and the area here will be equal for the same amount of time. That is only possible if the two velocities here are different. So when the planet is closer to the sun, it's moving a little bit faster compared to when it is further away from the sun. Remember that the only force that acts between the two celestial bodies, the sun and the planet, is the gravitational force. And the gravitational force does no work because it's always perpendicular to the trajectory of motion at any moment of time. So there is no net torque that acts on this planet, which means that the angular momentum must be conserved at all times as the planet orbits around the sun. And so the consequence of that is that the areas swept by the planet for the same amount of time are equal, and that only can happen when the two velocities here and here are different. So the velocity of a planet orbiting around the sun or any other star, for that matter, will not be constant everywhere around the orbit, unless that is a circular orbit.